Hello everyone. Once again, welcome to my YouTube channel Physics with Dr. Sanjay Bhargav. In our third video on two-dimensional motion, we would be dealing with uniform circular motion, the variables of circular motion like angular displacement, velocity, acceleration. We'll discuss about uniform circular motion, requirement of centripetal acceleration, centripetal force, and discuss non-uniform circular motion. So here we pick up with uniform circular motion. If a particle moves along a circular path with a constant speed, then its motion is said to be uniform circular motion. So a particle is supposed to move along the circle with uniform speed. The examples of uniform circular motion: motion of the tip of a hand of a clock. So every hand of the clock performs uniform circular motion. Motion of a point on the rim of a wheel rotating uniformly. We first calculate what are the variables of circular motion. The first variable of the circular motion is angular displacement. The angular displacement of a particle moving along a circular path is defined as the angle covered by the radius vector in a given interval of time. Here, at the time t is equal to 0, the position of the particle is p0. At the time t is equal to t1, the position of the particle is p1. It has traversed an angle theta with respect to the point p0. At a later time t is equal to t2, we are at the point p2. An additional angular displacement delta theta has been covered by the particle. Angle, we define it as the ratio of arc upon radius. So angular displacement is delta theta, and we define it by arc p1 p2 upon the radius r. And what is p1 p2? P1 p2 is nothing but the linear displacement represented by delta s. So angle delta theta must be equal to linear displacement upon the radius delta s upon r. So numerically we write delta theta as delta s upon r. Angular displacement is measured in terms of radian, and it is supposed to be a dimensionless quantity because it's the ratio of two distances, linear displacement and the radius. The second variable is angular velocity. We'll define average angular velocity and instantaneous angular velocity. So let a particle trace an angle theta 1 in the time t1 and an angle theta 2 in the time t2. Delta theta, that is angular displacement, would be theta 2 minus theta 1 in the time interval t2 minus t1. The figure shows the position p1 at the time t1 and position p2 at a time t2. The angular displacement delta theta is equal to theta 2 minus theta 1. How do we define average angular velocity? It is defined as the ratio of angular displacement to the time taken by the particle to undergo this displacement. So average angular velocity we write by two curly brackets and omega is equal to theta 2 minus theta 1 upon t2 minus t1, which can be written as delta theta upon delta t, and the unit of angular velocity radian per second. Instantaneous angular velocity omega. It is defined as the limiting value of the ratio delta theta by delta t when delta t tends to 0. So omega, the instantaneous angular velocity, will be equal to limit delta t tending to 0, delta theta by delta t, which can be written as d theta by dt. Uniform angular velocity. Uniform angular velocity, how do we define? The angular velocity of a body is said to be uniform when it covers equal angles in equal intervals of time, howsoever small these intervals may be. So a body is said to have uniform angular velocities if it is covering equal angles in equal intervals of time. What is the unit? Omega has a unit radian per second or second inverse. The dimensions are m0, L0, t power minus 1. Remember, angular velocity is an axial vector whose direction is given by the right hand thumb rule. What does the right hand thumb rule says? If the fingers of the right hand are curled in the direction of circular motion, then the thumb points in the direction of angular velocity. Another variable of circular motion is angular acceleration. Once again, we will be defining average angular acceleration and the instantaneous angular acceleration. How do we define average angular acceleration? It is defined as the ratio of change in angular velocity to the time taken by the particle to undergo this change. Let a particle have angular velocity omega 1 and omega 2 at the times t1 and t2 respectively. So we define average angular acceleration as change in angular velocity omega 2 minus omega 1 in the time interval t2 minus t1, which can be written as delta omega by delta t. Now, how do we define instantaneous angular acceleration? It is defined as the limiting value of the ratio delta omega by delta t when delta t tends to 0. So alpha we define as limit delta t tending to 0, delta omega by delta t, which can be written as d omega by dt. Then what is uniform angular acceleration? We can define it. Uniform angular acceleration of the body is said to be uniform if its angular velocity changes by equal amounts in equal intervals of time, howsoever small these intervals may be. So unit of alpha, radian per second square or second power minus 2. The dimensions m0, L0, t power minus 2. Now we'll find relationship between the various quantities. First of all, we are going to calculate relation between frequency nu, time period and omega. First we calculate relation between the frequency and the time period. Here nu is the frequency and is equal to number of revolutions per second. What is time period? T represents here the time period and is equal to the time taken to complete one revolution or rotation. So time taken to cover new revolutions is 1 second. So time taken to complete one revolution is 1 by nu of a second, but the time taken to one revolution is called the time period. So t would be equal to 1 upon nu, or frequency nu is equal to reciprocal of the time period. The product nu into t must be equal to 1. Now we calculate relationship between angular velocity omega, time period, and that is omega t relation and omega nu relation. Now, when a body completes one revolution, it travels an angle 2 pi radian and obviously takes a time equal to the time period. So omega can be written as angle traversed upon the time taken. So 2 pi is the angle traversed and t is the time taken. So omega into t is 2 pi. Remember, t is equal to 1 upon nu, so omega can be written as 2 pi nu. This gives me a relation between angular velocity and the frequency. Now, we like to calculate relation between linear and angular variables, that is v and omega. So we consider a particle moving along a circular path of radius r with angular velocity omega in anti-clockwise direction. So we have a particle moving in anti-clockwise direction. It is having a velocity v and angular velocity omega. It's moving from P1 point to P2 point and that linear displacement is s. V, tangential velocity of the particle. Arc P1, P2 of length s subtends an angle theta at the center. So theta would be equal to s upon r. So s would be equal to r theta. You can differentiate both the sides with respect to time. So ds by dt would be equal to r, that is radius constant, d theta by dt. And remember, ds by dt is nothing but velocity and d theta by dt is omega. So the relation is v is equal to r omega. In vector form, it can be written as v vector is equal to omega cross r. Similarly, we like to calculate a relation between angular acceleration and the tangential acceleration. So alpha is a representation of angular acceleration, at is a representation of tangential acceleration. We have just established a relation v is equal to r times omega. Differentiate both sides with respect to time, we get dv by dt would be equal to d by dt of r omega. R is a constant, so it can be taken out of the sign of differentiation. So it's written as r into d omega by dt. But what is dv by dt? That is tangential component. And what is d omega by dt? That is the angular acceleration. So at is equal to r alpha. How can we write in the vector form? It can be written as alpha cross r. Now let us pick up the discussion of uniform circular motion. When a particle moves along a circle with a uniform speed, a force is always required. This is because even though the speed remains the same, the velocity is changing due to change in direction. So at the point A, the direction of the tangent gives the direction of velocity, hence the direction of motion. So you can see at point A, B, C and D, at every point the direction of velocity is different. That means in circular motion, though the magnitude of the velocity may be same, but the direction of velocity is changing. The velocities at the point A, B and C and D are along the tangent. Every body has a directional inertia, so a velocity cannot change by itself, so we have to apply a force. This force must change the direction of velocity and not its magnitude. This is possible only if the force acts perpendicular to the direction of velocity. Since velocity is along the tangent, so the force has to be along the radius of the circle, because radius and tangent form a mutually perpendicular system. Now let us define centripetal force. A force which is required to move a body in a circular path with uniform speed. This force acts on the body along the radius and towards the center of the circular path. Now let us talk about centripetal acceleration. An acceleration which is directed along the radius and is always towards the center of circular motion is called centripetal acceleration. This arises due to change in direction of velocity in the uniform circular motion. So change in the direction of velocity is responsible for centripetal acceleration. Let us calculate a relation for centripetal acceleration. We consider an object which is moving with uniform speed v in a circle of radius r. Since the velocity of the object is changing continuously in direction, so acceleration of the object takes place. Here r and r dash be the position vectors and v dash be the velocities at the point p and p dash. The direction of velocity is always along the direction of the tangent at that point. The velocity vectors are shown in figure A1. Using triangle law, delta v can be obtained. So here it represents point P and P dash. The velocity is given by the direction of the tangents v and v dash. Here we have position vector r and r dash. Remember, P to P dash represents the displacement. So using triangle law, delta v is obtained in the figure A2. So we are having figure A1, figure A2. This represents the figure A1 and this represents figure B1. This represents A2, this represents B2. So what does the text say? It says using triangle law, delta v can be obtained in figure V2 here. In circular motion, velocity is perpendicular to the radius and v dash is also perpendicular to the radius. So delta v is also perpendicular to delta r. The average acceleration is along delta v. So direction of average acceleration is along the direction of change in velocity. So if average acceleration is perpendicular to delta r, if delta v is on the line bisecting angle between r and r dash, then it is directed toward the center of circle. So what we have shown here in this figure, the direction of delta r is along the direction of delta v. Correct? Figure B shows same quantities for a smaller time interval, delta v, and acceleration are again directed towards the center. In figure C, as delta t tends to 0 and the average acceleration becomes equal to the instantaneous acceleration. In the limit delta t tending to 0, delta r becomes perpendicular to r. Just see here. So this is the direction of velocity, this is the direction of acceleration. Radius, so acceleration is along the radius. Radius and velocity are forming a mutually perpendicular system under the limiting condition delta t tending to 0. So that is what we have said. In the limit delta t tending to 0, delta r becomes perpendicular to r. In this limit delta v tends to 0 and is perpendicular to v. So acceleration is directed towards the center at each point of the circular path. The magnitude of the acceleration can be calculated by limit delta t tending to 0 delta v upon delta t. In the figure A, in the triangles delta C, triangle CPP dash and the triangle IGH, these two triangles are similar. So the ratio of base to sides are equal. So delta v upon v would be equal to delta r upon r, or delta v can be written as v into delta r upon r. So acceleration would be limit delta t tending to 0 delta v by delta t. So limit delta t tending to 0. So delta v can be written as v delta r upon delta t, and r already existing here can be written as v upon r limiting value delta t tending to 0 delta r by delta t, which can be written as dr by dt. If delta t is small, delta theta will also be small. Then the arc PP dash will be nearly equal to delta r. So limit delta t tending to 0 delta r by delta t is equal to velocity v. So centripetal acceleration is equal to v square by r, can also be written as omega square r. Thus acceleration of an object moving with the speed v in a circle of radius r has a magnitude v square by r and is always directed towards the center, so called as centripetal acceleration. What does the word centripetal stand for? Means center seeking. Here v is equal to r omega, so centripetal acceleration can have a value v square by r or omega square r. Now we have certain important points here. In uniform circular motion, what happens? The magnitude of the velocity remains constant. The direction of the velocity vector, which is along the direction of the tangent, changes continuously. So circular motion is an accelerated motion. The magnitude of centripetal acceleration remains constant, but its direction continuously changes. Its direction is always perpendicular to the direction of velocity at that point. So in uniform circular motion, equations of motion are not applicable because it represents an accelerated motion. Now let us pick up non-uniform circular motion. Here we consider a particle moving along a circular path with variable speed. The acceleration A vector has two components, at and ar. At, the tangential component of the acceleration, which arises due to change in magnitude of velocity. At is equal to dv by dt. The second component is ar, the radial component of acceleration, which arises due to change in the direction of a velocity. And ar we have already calculated as v square by r. The total acceleration can be equal to the vector sum of the tangential and the radial acceleration. So total acceleration would be under root of at ka square plus ar ka square. At dv by dt ka whole square and ar v square by r ka whole square. Now let us pick certain examples to understand what we have done. A stone tied to end of a string 80 centimeter long is whirled in a horizontal circle with a constant speed. If the stone makes 14 revolutions in 25 seconds, what is the magnitude and direction of acceleration of the stone? So what is given here? The radius is given as 80 centimeter. The frequency is 14 upon 25 rotation per second. Omega is 2 pi nu. So 2 pi is 22 by 7 and the frequency is 14 by 25. So 88 by 25 radian per second. Now acceleration of the stone is omega square r. So 80 is the radius and 88 by 25 is omega whole square. It gives me 991.2 centimeter per second square. That gives me centripetal acceleration as asked in the question. A cyclist is riding with a speed of 27 km per hour. As he approaches a circular turn on the road of radius 80 meter, he applies brakes and reduces his speed at a constant rate 0.5 meter per second. What is the magnitude and direction of the net acceleration of the cyclist on the circular turn? Remember, here cyclist is applying the brake at the point A, at this place. Then tangential acceleration will act opposite to the direction of velocity. So tangential acceleration is given as 0.5 meter per second square and the centripetal acceleration v square by r. So 27 into 5 by 18 ka whole square upon 80 and gives me 0.7 meter per second square. As we have just learned, the total acceleration must be equal to under root of AC ka square plus AT ka square. Centripetal acceleration 0.7 ka whole square plus tangential acceleration 0.5 ka whole square. That will give me 0.86 meter per second square. That is the total net acceleration. Now here theta is the angle between tangential and the total acceleration. So tangent theta would be equal to AC upon AT. That is 0.7 upon 0.5, that is 1.4. So theta would be equal to 54 degree and 28 minutes with respect to the vertical. Calculate the angular speed of the hour hand of a watch and the earth about its own axis. The hour hand completes one rotation in 12 hours. So omega angular velocity would be theta upon t. So in one circular rotation it is 2 pi radian as the angular displacement and the time taken is 12 hours. So this would be 2 pi 12 into 60 into 60 converted into second. So the speed would be given by pi upon 21,600 radian per second. The earth completes one rotation about its axis in 24 hours. So omega can be written as theta upon t, which theta is 2 pi radian and the time taken is 24 hours, which can be written as 2 pi upon 24 into 60, that is pi upon 43,200 radian per second. Let us pick up another example. The angular velocity of a particle moving along a circle of radius 50 centimeter is increased in 5 minutes from 100 revolutions per minute to 400 revolutions per minute. Find the angular acceleration, linear acceleration. Here frequency nu1 is 100 upon 60 rotation per second, nu2 is 400 upon 60 rotation per second, radius is 50 centimeter and the time taken is 5 minutes, converted to second is 300 seconds. Angular acceleration would be omega 2 minus omega 1 upon the time taken, that is 2 pi nu2 minus nu1 upon t. 2 pi, this is 400 upon 60, 100 upon 60. So here we are in a position, so time taken is 300 and the answer gives me angular acceleration as pi by 30 radian per second square. For linear acceleration, a would be equal to r times alpha. So r is 50 and the acceleration is pi by 30. So it is 5 pi upon 3 centimeter per second. Hope you have clearly understood the basic concepts of uniform circular motion, the various variables required for explaining circular motion. If you have enjoyed uniform circular motion with us, then you are requested to subscribe my channel, like my video and comment on my video. You are also requested to press the bell icon button so that you can receive the notifications of new videos in time. Thank you very much.